Hello there, and welcome to the Sleepy Space Channel. The universe did not build a single wall between us and the stars. It built a chain of them, and every link is welded to the next. The distance alone would take our fastest spacecraft 73,000 years to cross to the nearest star. Try to solve that with speed, and a grain of dust smaller than a human hair strikes the hull with the force of a bomb, while the energy bill climbs past the output of entire civilizations. Try to solve it with patience instead, and time goes quietly to work on bodies, machines, and memory. Tonight we follow the whole chain, link by link, through distance, time, energy, radiation, dust, and the strange absolute limit of light itself. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is something you need to carry. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. Every civilization that ever looked up at a clear night sky asked the same question, and the question has never changed. What is out there, and could we ever go? The Polynesian navigators crossed thousands of miles of open ocean with no instruments at all, reading the positions of stars, the rhythm of wave patterns against the hull, the flight paths of birds at dusk, and subtle shifts in the color and temperature of the water. They held all of that knowledge in memory, passing it from master to apprentice across dozens of generations, and it carried them safely between islands separated by more empty water than most people ever see in a lifetime. Around the ancient Mediterranean, astronomers imagined the heavens as a set of nested crystal spheres, each one carrying its points of fire in slow procession across a dome of darkness. In early China, careful observers recorded new stars that appeared without warning in the night, bright enough to see with the unaided eye, and wondered what force could make a star flare and fade. In Australia, some of the oldest continuous cultures on Earth read the sky in an unusual way, finding their constellations not in the stars themselves, but in the dark spaces between them, building stories from the shape of absence. Every culture, on every continent, in every century, felt the same quiet pull. The stars were there, and something in us wanted to answer them. That desire never faded with knowledge. It grew sharper. Modern astronomy inherited the ancient longing and added something the ancients never had, which is precision. We learned to measure the actual distances to the stars, not guess at them. We learned to weigh them, to read their temperatures from their colors, and to detect the small, dark worlds circling them. Astronomers have now confirmed more than 5,000 planets orbiting other stars, and the count keeps rising. Statistically, the numbers suggest something remarkable in its calm way. There appear to be more planets than stars in our galaxy, which means hundreds of billions of worlds in the Milky Way alone, most of them still uncatalogued, drifting around suns we have never examined closely. Some of those worlds sit in what astronomers call the habitable zone. The idea behind that phrase is simple and rather beautiful. Around every star there is a band of distances where the warmth arriving at a planet's surface is neither too much nor too little, so that water, if it exists there, could remain liquid. Closer in, the oceans would boil away. Farther out, they would lock into ice. In between lies the region where seas can stay seas. The nearest confirmed planet beyond our solar system orbits the nearest star to the Sun, a small red star called Proxima Centauri, a little over 4 light-years away. Farther off, roughly 40 light-years from here, a dim and cool red star holds 7 planets close around it, several of them near Earth's size, a whole compact family of worlds arranged like a miniature solar system. We can even begin to study their air. When a planet crosses the face of its star, a tiny fraction of the starlight filters through the thin ring of atmosphere at the planet's edge, and every gas in that atmosphere absorbs its own characteristic colors from the light. By reading which colors go missing, telescopes can identify water vapor, carbon dioxide, methane, and other molecules on worlds so distant that the planets themselves appear as nothing at all in an ordinary image. It is a shadow of a shadow, and yet it is real chemistry, measured across trillions of miles. Astronomers are careful with what such measurements can promise. Oxygen, for instance, feels like the signature of life, and yet a lifeless world can build an oxygen-rich sky through slow chemistry alone, as starlight splits water apart and the hydrogen drifts away into space. A promising reading is an invitation to look closer, never a confirmation. Still, the direction of the work is unmistakable. The destinations are real. The worlds exist. But some of them may have rain and shorelines and weather. There are cautions folded into the catalogue, and they are worth hearing in a quiet voice. Many of the most promising temperate worlds orbit red dwarf stars, the small, cool, long-lived stars that make up most of the galaxy's population. A planet warm enough for liquid water around such a dim star must huddle close to it, and a planet that close tends to become tidally locked, with one face turned forever toward its sun and the other forever away. One hemisphere lives in permanent afternoon, the other in permanent night, and the habitable ground, if there is any, may be a ring of eternal sunset between them. Red dwarfs also flare. The planet around our nearest neighbor star receives outbursts far stronger than anything our sun sends toward Earth, and over long ages, those storms may strip a world's atmosphere thin. Even the word rocky is an inference. Astronomers measure a planet's size and mass and calculate its density, but a world that seems rocky by the numbers may in truth be drowned, an ocean planet with no land anywhere, its water running down for 100 kilometers before touching stone. Our instruments are honest about what they can see, and what they can see is limited. And the search continues to widen anyway, because it should. Some astronomers suspect the most comfortable homes for life may cluster around orange dwarf stars, a middle class of suns that are calmer than the red dwarfs and longer-lived than stars like our own. The census is biased in ways the astronomers understand well. Large planets close to their stars are the easiest to find, while small, cool worlds like Earth are the hardest, which means the current catalogue almost certainly undercounts the very kind of planet we care most about. The true number of Earth-like worlds is likely higher than anything yet written down. Imaging one of them directly next to a sun-like star has been compared to photographing a firefly resting beside a lighthouse from thousands of kilometers away, and yet the telescopes keep improving and the firefly keeps getting closer to visible. So the question has never been whether there is somewhere worth going. There is. The sky is full of destinations, more of them confirmed every year, some of them close enough that their light reaches us in the span of a childhood. The question is different, and it is older, and it sits underneath everything this channel loves to explore. The question is whether the universe will let us make the trip. And the answer, worked out slowly over the past century by people doing careful arithmetic with distance and energy and time, has a strange and quietly sobering shape. The universe has not placed one wall between us and the stars. It has built a chain of them, and the links are welded to one another. Distance forges the first link. Distance forces a choice between traveling slowly and traveling quickly, and each of those choices forges its own further links, barriers of biology and machinery and energy and dust, each connected to its neighbors, so that easing any single one tightens another. That chain is what the rest of tonight is for. We will walk its length, link by link, unhurried, and see how each barrier arises from the one before it. But every chain has a first link, and the first link here is the simplest and the largest. Before biology, before energy, before any question of engines, there is the plain matter of how far away the stars actually are. The numbers involved are not merely big. They belong to a different category of big, a kind that human minds were never built to hold, because nothing in our long history ever required us to hold it. Our ancestors needed to judge the distance a body could walk in a day, the width of a valley, the reach of a coastline. The distance to the nearest star answers to none of that. So we will take it slowly, with comparisons small enough to carry, and let the true scale of the gulf settle in gently, one measure at a time. Right now, as you listen, the farthest object human beings have ever launched is drifting through the darkness between the stars. It is a spacecraft roughly the size of a small car, and its name is Voyager 1. It left Earth nearly 50 years ago on a mission to study the outer planets, and it did that work beautifully, sending home the first close portraits of giant worlds and their strange moons. When the last flyby was finished, nothing stood in its way, and nothing could call it back, so it simply kept going, outward, on the same heading, at the same speed, year after year after year. In time, it crossed a boundary called the heliopause, the place where the sun's outflowing wind of charged particles finally gives way to the thin gas that fills the space between stars. Past that line, Voyager 1 became the first machine in history to sample the interstellar medium directly. It has been out there ever since, alone, its instruments slowly going quiet, its radio whisper still arriving at the great listening dishes of Earth. Voyager 1 travels at roughly 17 kilometers every second, which is about 38,000 miles per hour. That is fast by any measure a human being has ever applied to a moving object. At that speed, you could circle the entire Earth in about 40 minutes. You could reach the Moon in about 6 hours. You could cross the gap between Earth and Mars, at their closest approach, in under 2 months. And Voyager has been moving at that pace, without pause, for nearly half a century. In all that time, it has covered a distance that light itself could cross in about 1 day. 1 light day. A radio command sent from Earth in the morning spends the entire day and night traveling and reaches the spacecraft the following morning. The reply takes just as long to come home. Our farthest traveler, after 50 years, is 1 day of light away. Now hold that number gently beside another one. The nearest star to our Sun, Proxima Centauri, is not 1 light day away. It is about 4¼ light years away. A single light year contains 365 light days, so the nearest star sits more than 1,500 light days from here. Voyager 1, after the longest continuous journey in human history, has crossed roughly 1 part in 1,500 of the distance to the closest star there is. If the spacecraft were aimed directly at Proxima Centauri, which it is not, it would arrive in something like 73,000 years. It helps to let that span breathe for a moment. 73,000 years ago, modern humans still shared the world with Neanderthals. Everything we tend to mean by civilization, all of agriculture, writing, cities, mathematics, sea trade, industry, and flight, fits comfortably inside the most recent 10,000 years. Voyager would need 7 of those entire spans, laid end to end, to drift from our Sun to its nearest neighbor. There is a detail that makes the distance stranger still, in its quiet way. Voyager 1 has not actually finished leaving home. Crossing the heliopause was real, and it mattered, but the Sun's true domain reaches far beyond that boundary. Our star holds an enormous shell of icy bodies in its gravitational grip, a structure called the Oort cloud, the deep reservoir from which long-period comets fall. That shell is thought to begin around 2,000 astronomical units from the Sun, where 1 astronomical unit is the distance from Earth to the Sun, and it may extend outward to as much as 100,000 astronomical units, which is getting close to 2 light-years. Voyager 1 is currently more than 160 astronomical units out, over 15 billion miles from home, and that places it far short of even the inner edge of the cloud. It will not enter the Oort cloud proper for centuries. It will not pass beyond the far edge of the Sun's gravitational sphere for roughly 30,000 years. The heliopause, it turns out, was never the door. It was a curtain hanging inside a much larger room, and our farthest machine has only just pushed through the curtain. The door is 30,000 years ahead of it, and the nearest neighboring star waits tens of thousands of years beyond that. Numbers this large resist the mind, and that is not a personal failing. The human brain was tuned to judge the distances a body can walk and the horizons an eye can scan, so the honest approach is to shrink the problem until it fits on a map we know. Imagine, then, that we could scale the whole solar system down until the Sun became a basketball resting on a sidewalk in New York City. At that scale, Earth is a grain of sand orbiting about 26 meters away, roughly 85 feet from the ball. Jupiter is a marble a block and a half down the street. Neptune, the outermost major planet, is a small pea sitting about 800 meters off, half a mile from the basketball. The entire familiar solar system, every planet and moon and ring, fits within one modest walk through a single neighborhood. Voyager 1, after its 50 years of flight, has made it a couple of miles past the pea. It is still, on this map, well inside the city. And the nearest star, on this same map, is another basketball resting on a sidewalk in Honolulu, more than 4,000 miles away across an ocean. Between the two basketballs, there is nothing. No waypoints, no shelters, no islands. A few grains of sand cluster near one ball, and then the map is empty the whole way to the other. If anything, that picture is too generous, because the space between the stars is emptier than any emptiness we can make. The interstellar medium averages about 1 hydrogen atom in every cubic centimeter. The air you are breathing right now packs about 25 billion molecules into that same small volume. The finest vacuum chambers ever built on Earth, the pride of the best laboratories, still hold millions of molecules per cubic centimeter, which makes our best artificial nothing millions of times more crowded than the natural nothing between the stars. Interstellar space is not simply dark and cold. It is absence refined almost to perfection. One atom here, one atom there, and light passing through on its long errands. For completeness, it is worth asking whether anything we have built moves faster than Voyager, and the answer is yes, briefly and in a special place. The Parker Solar Probe, built to study the Sun at close range, swings so near the solar surface that it briefly exceeds 190 kilometers per second, fast enough to cross the continental United States in about 20 seconds. It is the fastest object our species has ever made. And even at that extraordinary peak speed held steady the whole way, the trip to Proxima Centauri would take about 6,700 years, a span longer than the age of the pyramids. The probe cannot hold that speed anyway. It earns it only by falling deep into the Sun's gravity, again and again, in a place we cannot take a voyage. The steadier travelers tell the truer story. New Horizons, which flew past Pluto, cruises at about 14 kilometers per second. The two Pioneer probes drift outward at 11 and 12. These are our champions, and none of them will approach another star for tens of thousands of years. A light year, written out plainly, is about 9.5 trillion kilometers, and the Gulf to Proxima holds more than 4 of them. And this, remember, is the shortest interstellar gulf we have. The Milky Way as a whole spans about 100,000 light-years, so the gap to our nearest neighbor is the single smallest step on a staircase that climbs beyond all counting. Even the identity of that neighbor is temporary. The stars around the Sun are all in motion, drifting on their own long orbits through the galaxy, and over tens of thousands of years, the arrangement of our neighborhood slowly changes. In the deep future, other stars will wander closer than Proxima is now, and then wander away again. The map is patient, but it is not fixed. One more comparison, and then we can set the ruler down. If the whole solar system out to Neptune were shrunk to the size of a single coin, the nearest star would be another coin resting about 700 meters away, with nothing between them but floor. This is the first wall, the wall of distance, and everything else tonight grows out of it. Because there are, in the end, only 2 honest responses to a gap this wide. You can cross it slowly and pay in time. Or you can try to cross it quickly and pay in ways we will come to. The chain begins with that choice. It would be natural to assume that a voyage to another star is simply a longer version of the voyages we already make, that interplanetary travel and interstellar travel sit on the same scale, one merely farther along it than the other. The truth is stranger and more interesting. They are not different distances of the same journey. They are different categories of problem, as different as walking across a room and walking across a continent, and the difference is worth unfolding slowly because it explains why everything humanity has achieved in space so far, remarkable as it is, tells us almost nothing about crossing to the stars. Consider what has actually been done. Rovers have landed on Mars and driven for years across its cold deserts, photographing sunsets that fade to blue instead of red. A probe has descended through the orange haze of Titan, the great moon of Saturn, and come to rest beside lakes of liquid methane. Spacecraft have flown past every major planet in the solar system, out to Pluto and beyond, returning portraits of worlds no telescope could resolve. Observatories have been parked at quiet gravitational balance points far from Earth, where they drift in step with us and stare into the deep. These are real triumphs, earned through decades of care. And every one of them shares a single feature that is easy to overlook. They all happened inside a region where distances are measured in light minutes and light hours. That measurement matters more than any other single fact in spaceflight. A radio signal from Earth to Mars takes between about 4 and 24 minutes, depending on where the 2 planets sit in their orbits. A signal to the outer planets takes hours. Those delays are inconvenient, but they are workable. Mission controllers can send a command in the morning and hear back before the day ends. Software can be repaired from the ground. A trajectory can be nudged while there is still time for the nudge to matter. When a rover on Mars develops a fault, engineers can diagnose it, write a fix, test the fix, and transmit it, all within a day or 2. The machine, however distant, remains inside a working relationship with the people who built it. That relationship, more than any engine, is what has made the exploration of the solar system possible. Every mission ever flown has leaned on it. The spacecraft supplies the presence, and Earth supplies the judgment, the memory, the repairs, and the patience. Now stretch the distance and watch the relationship dissolve. The gap to Proxima Centauri is roughly 700,000 times the distance from Earth to Mars at their closest approach. That is not an increase. It is a multiplication by nearly 1,000,000, a jump of almost 6 orders of magnitude, and problems do not survive a jump like that unchanged. A fault that occurs 4 light-years from home is reported to Earth 4 years after it happens. The earliest possible reply, carrying the cleverest possible fix, arrives 8 years after the trouble began. Every additional light-year of distance adds 2 more years to that round trip. Mission control, as a concept, simply stops existing. There is no conversation anymore, only a very slow exchange of letters between parties whose situations have changed completely by the time each letter arrives. Whoever rides a ship into that gulf must carry the judgment, the memory, and the repairs along with them, because Earth's help will always arrive years too late to matter. Resupply dissolves in the same quiet way. Within the solar system, a stranded mission can in principle be reached, and the space station above our heads is sustained in exactly this fashion, by a steady procession of cargo vessels rising from Earth carrying water, food, oxygen, and spare parts. But nothing can resupply a ship that is already crossing the interstellar gulf, and the reason is almost elegant. To catch a departed ship, a cargo vessel would have to be meaningfully faster than the ship it is chasing. And if a meaningfully faster vessel existed, it would not be chasing anyone. It would have been the ship. Whatever leaves for another star leaves complete, or it leaves lacking, and the lack can never afterward be made good. Every gram of food, every liter of water, every medicine, every replacement component for every machine must either be aboard on the day of departure or be manufacturable on board, from stores carried along during the voyage itself. Rescue dissolves last, and most completely. If something goes wrong 2 light-years out, no one is coming. There is no version of the technology, no reading of the physics in which anyone is coming. The travelers are alone with what they brought, in the largest sense those words have ever had. Even hearing from such a ship becomes an act of extraordinary delicacy. Communication across the solar system already depends on a global network of enormous radio dishes, antennas the size of buildings, straining to catch signals from probes whose transmitters are no stronger than a refrigerator bulb. The whisper from Voyager 1 arrives at those dishes carrying a tiny fraction of a billionth of a watt, and engineers lift it out of the noise through patience and mathematics. Stretch the range from light hours to light years, and the whisper thins toward silence. A crewed vessel could carry a stronger transmitter, but the delay does not care about power. However loud the voice, the words still take years to arrive, and years to answer. It is worth pausing on what the numbers imply about speed as well, because they close the last comfortable door. The chemical rockets that carry everything we launch produce exhaust moving at 3 to 5 kilometers per second. The finest ion engines ever flown, gentle thrusters that push spacecraft patiently for years, reach exhaust velocities of 30 to 50 kilometers per second. Now, set those figures against the scale of the problem. 1% of the speed of light is 3,000 kilometers per second. Not the halfway mark, not the goal, just 1% of it, and it already stands far beyond every engine we possess. And even a ship that somehow reached that speed would still spend more than 420 years traveling to the nearest star. 4 centuries is a span in which, on Earth, empires have risen, flourished, and vanished entirely. The Apollo crews reached the Moon in about 3 days. A crewed voyage to Mars takes many months. The step from Mars to Proxima multiplies the road by hundreds of thousands, and no strategy that worked on the shorter road survives the multiplication. Think about what that self-reliance actually asks for, item by item. The ship must navigate on its own, sensing its position against the slowly shifting background of stars and correcting its course without waiting for confirmation from home. It must practice its own medicine, from filled teeth to major surgery, with whatever skill and equipment came aboard. It must settle its own disputes, because there is no court to appeal to and no authority that can arrive to enforce a ruling. It must teach its own children everything the mission depends on. Each of those functions exists on Earth as an entire profession, an entire institution, refreshed constantly by new people and new knowledge. On the ship, each one is a small group of mortal individuals and a library and nothing more. So the tools that conquered the solar system do not transfer. Real-time control does not transfer. Resupply does not transfer. Rescue does not transfer. What remains is a new kind of requirement, one that no vehicle in history has ever had to meet. A ship bound for another star cannot merely be a vehicle. It must be a self-contained world, carrying its own workshop and hospital and farm and school, its own laws and its own long memory, everything a civilization needs, compressed into a hull and sealed against the dark. And the moment the requirement is stated that way, the chain of barriers begins to fork. Because there are two ways to attempt a self-contained world between the stars. You can build one that endures for centuries and crosses slowly. Or you can build one that moves so quickly that endurance is beside the point. The slow road comes first, and it looks, at first sight, almost wise. The slow road begins with a thought that feels almost like wisdom. If the stars cannot be reached quickly, then perhaps they can be reached patiently. If a single lifetime is not enough for the crossing, then let the crossing take many lifetimes. Build a vessel large enough to carry not a crew, but a community. Stock it with everything a small civilization might need. Launch it toward the nearest star at whatever speed honest engineering can provide, and accept, calmly and in advance, that the people who board it will never arrive. Their children will be born on the way. Their grandchildren will inherit the corridors and the work. And someday, generations down the line, descendants who have never seen Earth, who know it only as a story told by the old and a color in the archive, will feel the engines turn for the first time in centuries and watch a new sun grow bright ahead of them. This is the generation ship, and it is the oldest serious answer to the interstellar question. The idea has been with us for about a century. It was first imagined as a kind of slow ark, a seeded world with engines, carrying not merely passengers but an entire ecology, closer in spirit to a drifting garden than to a vehicle. Storytellers took it up and furnished its interior, imagining societies that forgot they were aboard a ship at all, mistaking the hull for the sky. Engineers took it up as well, and more rigorously. There have been serious, patient design studies of multi-generation vessels, whole research programs asking how large the population should be, how the air should circulate, how the decks should be arranged, how a village works when the village is sealed inside a can and the can is falling between stars. The idea keeps returning, decade after decade, because it appears to ask nothing impossible of physics. No exotic speeds. No new laws of nature. Just a ship that lasts, and a people who endure. Patience, it seems, can be substituted for power. But before examining whether a ship can last and a people can endure, it is worth asking precisely how much patience the plan actually requires, because the word slow hides an enormous range. The most powerful propulsion concept ever seriously engineered was a vessel designed to ride a chain of nuclear pulses, detonations set off behind a massive pusher plate, each one shoving the ship a little faster. On paper, with a vehicle of enormous size, such a machine might work its way up to a few percent of the speed of light. Take the optimistic end of that range, 5%, and the arithmetic turns almost kind. At 5% of light speed, the crossing to Proxima Centauri takes roughly 85 years. That is one long human lifetime, or two short ones. A child aboard at launch could, with luck, watch the arrival through old eyes. Of all the numbers in tonight's story, that one comes closest to hopeful. But the hope needs qualifying, gently, from two directions. First, that vessel was never built, and its method, riding controlled detonations by the thousand, presents difficulties beyond the merely technical. Second, and more telling, everything actually available or nearly available falls short of that mark by an enormous margin. The nuclear systems being developed today for journeys within the solar system, thermal rockets and electric drives of real sophistication, top out at speeds that are orders of magnitude below even 1% of light speed. For any propulsion humanity plausibly commands in the coming century, the honest transit time to the nearest star is not 85 years. It is somewhere between many centuries and many tens of thousands of years. The generation ship, in its realistic form, is not a vessel that must work for one long lifetime. It is a vessel that must work, without interruption and without outside help, for longer than most civilizations on Earth have existed. Let the shape of that requirement settle for a moment. The ship must hold its air for longer than any building has held its roof. It must run its machines for longer than any machine has run. It must keep its society whole for longer than most societies have kept their names. And it must do all of this in total isolation, sealed against a vacuum colder and emptier than anything on Earth, with no deliveries, no visitors, and no second chances. A vessel like that is not really a ship at all. It is a world, deliberately small, and everything we know about worlds suggests that smallness is the hard part. A planet forgives. It has oceans to buffer its chemistry, forests to steady its air, room for populations to rise and fall without vanishing. A hull forgives nothing. Every cycle must close, every part must last or be replaceable, every skill must be taught again to every generation, forever. And there is a property of the slow road that deserves to be named early, because it will follow us through the next several parts of tonight's journey, like a quiet refrain. Every difficulty the generation ship faces grows with the length of the voyage. The radiation that seeps through the hull accumulates year by year, so more years mean more harm. The closed garden that feeds the crew drifts further from balance the longer it runs. The machinery wears with every decade. The society strains with every generation. The knowledge fades with every handoff from teacher to student. Whatever trouble time can cause, more time causes more of it. This means the slow road cannot be made safer by taking it more slowly. Slowing down, which sounds like caution, is actually the opposite. A 300-year crossing is harder than a 100-year crossing in every single dimension at once. A 3,000-year crossing is harder still, and a 30,000-year crossing, the honest figure for the engines we actually possess, asks for endurance so far beyond anything demonstrated by any human institution that the request loses meaning. On the slow road, patience is not a resource. It is the toll. Some sense of scale helps here, drawn from the design studies themselves. The populations proposed for such vessels typically run from a few hundred people to a few thousand, a number balanced carefully between two pressures. Too many, and the ship's farms and air systems cannot carry the load. Too few, and the community becomes fragile in ways that have nothing to do with machinery. because a village must fill every essential trade, every generation, from doctors to electricians to teachers, and a small village has no spare people. Population studies of long isolation suggest that somewhere between 500 and 5,000 individuals is the plausible floor for a community meant to persist indefinitely on its own, and even at the upper end, the margin is thin. For comparison, the longest-lived great empires of the ancient world held together for roughly 5 centuries, and they had a whole planet to draw on, with trade at their borders, new people arriving, and room to make mistakes. The ship has none of those cushions. It asks a village the size of a small town to outlast an empire, sealed in a container, on the first attempt. Even the choice of where to go becomes strange under this much time. A destination selected today must remain worth reaching for the entire duration of the voyage, and the voyage may outlast the language in which the destination was chosen. The star must stay quiet. The planet must stay habitable. The reasons for going must stay persuasive to people not yet born, who never agreed to any of it. Nothing about the plan is allowed to age, and everything human ages. None of this, by itself, settles the question. It only frames it honestly. The generation ship does not sidestep the barriers between the stars. It gathers them into a single long test, and the test has several distinct sections, each one capable of failing the whole. In the parts ahead, we will walk through them one at a time, unhurried. The radiation that falls through everything. The quiet rebellion of bodies, built for a world with weight. The sealed garden that must never stumble. The machines that must never stop, and the knowledge that must never fade. And at the end of it all, waiting patiently, the question of what is actually there when the engines finally fire again. The first of these tests is the most invisible, and it begins the moment the ship leaves the shelter of the sun. The first thing that troubles a generation ship cannot be seen, heard, or felt. Beyond the shelter of Earth's magnetic field and its deep blanket of air, space carries a steady weather of radiation, and a vessel between the stars stands out in that weather for centuries. The radiation comes in 2 broad kinds. The first is the sun's own contribution, sudden storms of fast protons thrown outward during solar outbursts. These are intense but brief, lasting hours or days, and a ship still near a star can be designed around them, with a small, heavily protected room where the crew shelters until the storm passes, the way travelers on Earth wait out weather. The second kind is deeper, stranger, and far more patient. It is called galactic cosmic radiation, and it does not come from any one place. It comes from everywhere at once. Galactic cosmic rays are the nuclei of atoms, mostly single protons but including nuclei as heavy as iron, that have been flung across the galaxy at nearly the speed of light by the most violent engines the universe operates. Exploded stars, collapsed stars, the churning regions around black holes. They arrive from all directions, at all times, in a thin, continuous drizzle that never strengthens into a storm and never stops. Each individual particle is unimaginably small, and yet a single heavy nucleus among them can carry the kinetic energy of a well-thrown baseball, compressed into something smaller than an atom. When such a particle passes through living tissue, it does not bruise. It drills, leaving a track of broken molecules through thousands of cells in a line, the kind of damage a body's repair systems were never tuned to expect. On the surface of the Earth, we are almost perfectly protected from this drizzle. The planet's magnetic field turns most of the particles aside, and the atmosphere absorbs most of what gets through, so that a person standing on the ground receives only a few thousandths of a sievert each year from the sky, a dose the body shrugs off. Astronauts on the space station orbiting inside the magnetic field but above most of the air, receive many times more, and their careers are carefully measured against it. But in true interstellar space, past the sun's own protective bubble, there is no field and no air. Out there, the unshielded dose from galactic cosmic rays alone rises to roughly 0.6 of a sievert every year, and sometimes more, depending on the state of the sun's distant magnetism. At that rate, within 5 to 10 years, every person aboard exceeds the lifetime radiation allowance set for professional astronauts, the most carefully monitored travelers our species has. And the voyage, remember, is not 10 years long. It is centuries. What does such exposure do, slowly, over a life? The picture assembled from careful laboratory work is quiet and unsettling in equal measure. Animals exposed to simulated cosmic radiation at doses resembling a long, deep space voyage show lasting changes in the fine structure of the brain. The regions responsible for forming new memories slow their renewal. Damaged patterns persist rather than healing. Alongside the neurological findings sit the more familiar tolls: higher lifetime risks of cancer, gradual harm to the heart and blood vessels, a general accumulation of cellular injury that medicine can watch but not reverse. None of this arrives as an event. There is no day on which it happens. It is simply a tax, collected continuously from everyone aboard for the entire duration of the crossing. The natural response is shielding, and here the physics turns genuinely strange because the obvious solution makes the problem worse. Intuition says that if radiation is falling on the ship, one should thicken the walls, and metal feels like protection. But when a galactic cosmic ray strikes a thick metal hull, it does not politely stop. It shatters, and it shatters the atoms of the wall along with it, spraying a shower of secondary particles, neutrons and protons and fragments of nuclei, onward into the interior. This cascade is called spallation, and its products can be more damaging to living tissue than the original particle would have been. Past a certain thickness, adding more aluminum or steel actually raises the dose the crew receives. The wall becomes a participant. Among the secondary particles, neutrons are especially unwelcome guests because they carry no electric charge, slip deeply through most materials, and are stopped well by almost nothing except large amounts of hydrogen. That last fact points toward the real solution and toward its price. The materials that shield well against cosmic radiation are the hydrogen-rich ones: water, certain plastics, liquid hydrogen itself, substances whose small light nuclei absorb and slow the particles without shattering into dangerous fragments. Effective protection means wrapping the entire habitable volume of the ship in meters of such material. Designers have long noticed the one graceful note in this arrangement, which is that a ship must carry great stores of water anyway, so the drinking supply can double as armor, tanks wrapped around the sleeping quarters so that the crew rests inside their own reservoir. It is an elegant image. It is also thousands of tons. Shielding on this scale adds enormous mass to the vessel, and every ton of it must be accelerated to cruising speed along with everything else, then slowed again at the far end. Protection is never free. It is paid for in fuel, and as we will see when the chain brings us to the fast road, fuel is paid for in more fuel. The armor competes directly with the engines. Thicken one, and you starve the other. We do not have to guess at the scale of the problem, because we have begun to measure it directly. Instruments have ridden along on voyages to Mars, quietly counting every particle that passed through them during the months of cruise, and the results are sobering in their modest way. A single one-way transit to Mars, a journey of well under a year, already delivers an appreciable fraction of an astronaut's entire career radiation allowance. That is the toll for the shortest interplanetary crossing we seriously plan, taken once. The interstellar traveler takes that toll every year, for life, and then bequeaths the arithmetic to children who never agreed to it. The measurements were meant to prepare us for Mars, and they do, but read at interstellar scale, they carry a second, quieter message about what centuries in the open would mean. There is a further wrinkle, almost too quiet to notice. The drizzle of cosmic rays is not perfectly constant. The sun's far-reaching magnetic bubble, even far out, deflects a portion of the galactic radiation, and that bubble breathes over a cycle of years. When the sun is active, the bubble swells and the deep space dose falls. When the sun rests, the shield thins, and interstellar space grows harsher. A ship, planning a voyage of centuries, cannot choose a good decade to travel. It will pass through every kind of decade there is. Electronics suffer alongside the crew, in their own fashion. The chips that run a modern spacecraft are etched fine, and a single heavy particle passing through can flip a stored value or burn a microscopic channel. The remedy is radiation-hardened design, circuits made larger, simpler, and slower on purpose, trading generations of performance for durability. A starship's computers would be sturdy and plain, and even they would age under the drizzle, accumulating small scars, year over year, for centuries. And for a generation ship, the deepest cost may be the one that passes between generations. Radiation damages the molecules of inheritance themselves. Over a voyage of centuries, harm to the population's genetic material accumulates not only in bodies, but in the line of descent, mutations gathered in each generation and handed to the next. Medicine aboard could watch for it and soften it, but nothing aboard could stop it. No experiment in history has followed 10 or 20 human generations under such exposure, for the simple reason that there has never been a way or a need to try. The travelers who stepped aboard would be, in the most literal sense, the beginning of an experiment with no precedent and no control group. Already the shape of the chain is visible in this single link. The radiation cannot be avoided, only absorbed, and absorbing it costs mass, and mass costs speed, and lost speed lengthens the voyage, and a longer voyage means more years of the very radiation the armor was meant to defeat. The links pull against each other, and this is only the first of the slow road's quiet tolls. The next one is stranger still, because it comes not from the depths of the galaxy, but from inside the travelers' own bodies, which were built, every bone of them, for a world they have left behind. Every human body is a record of the world that made it. 4 billion years of life on Earth unfolded under one steady, unchanging condition, the constant downward pull of the planet's gravity, and every structure in us assumes it. The architecture of the skeleton, the strength of the heart, the plumbing of the blood, the fine balance organs of the inner ear, all of it was tuned against that one reliable force. Gravity is so constant on Earth that no person in history has ever had to think about it, and that is precisely why its absence is so strange. Take the force away, and the body does not simply float. It begins, quietly and methodically, to take itself apart. We know this because people have lived in weightlessness, in orbit above the Earth, for months at a stretch, and their bodies have been measured with great care. The pattern is consistent. The load-bearing bones, the hips and the spine, lose roughly 1 to 2% of their mineral density every month, dissolving from within like a structure whose builders have concluded it is no longer needed. Muscles shrink, especially the deep muscles of the legs and back, whose entire purpose is holding a body upright against a pull that is no longer there, and they shrink despite exercise programs of 2 hours every day. The heart, relieved of the work of pumping blood uphill, weakens and grows rounder, remodeling itself toward the easier job. And the body's fluids, no longer drawn downward, drift headward instead. Faces grow puffy while legs grow thin, and the shift raises the pressure inside the skull. That pressure presses in turn on the optic nerve and gently deforms the eyeball itself, and some travelers return from long stays with their vision permanently changed. The balance system adapts in its own way, learning within days that up and down have stopped meaning anything, and then must painfully relearn the old rules on return. For the crews of the space station, all of this remains manageable because their stays end. They come home within months, gravity resumes its instruction, and the body slowly rebuilds, though the recovery is imperfect and some of the bone never fully returns. A generation ship offers no return. Weightlessness, or whatever partial substitute the ship provides, is not an episode in the travelers' lives. It is their lives. They are born into it. Their children grow up in it, form their bones in it, learn to move in it. Over generations, a population living without adequate weight would drift, body by body, away from the form that Earth shaped and towards something lighter, frailer, and less able to bear load. The people who finally arrived at a new world, having survived everything else the voyage could do, might step onto its surface and find that its gravity, the most ordinary thing a planet has, is more than their inherited bodies can carry. There is a fix, and it is honest physics rather than wishful thinking. Galaxies will continue to drift. The stars overhead may appear eternal, but the great web of galaxies is always in motion. Rotate the habitat, and the same effect that presses passengers outward on a turning carnival ride will press the crew against the hull, and that steady outward press can stand in for weight. Rotation genuinely works, and it has been part of serious design for as long as the designs have existed. But the engineering asks a great deal, and the asking is worth hearing in detail. The trouble is the human inner ear, which is a small, exquisitely sensitive instrument, and which objects to being spun. In a rotating habitat, moving objects seem to swerve, dropped things curve as they fall, and turning one's head can set the world tilting. These effects grow more severe the faster the spin, and human tolerance runs out at roughly 2 rotations per minute for comfortable, indefinite living. Spin slower, and the discomfort fades, but a slow spin generates only a weak substitute for gravity, unless the habitat is very large, because the outward press depends on both the rate of turning and the radius of the turn. Work the numbers for a full Earth weight at a tolerable spin, and the answer comes back plainly. The rotating structure needs a radius of at least about 225 meters, which means a wheel nearly half a kilometer across. No rotating habitat of any size has ever been built. The only artificial gravity data our species possesses comes from short sessions on spinning platforms in laboratories on the ground. Now place that wheel on a starship and watch the chain pull tight again. A structure half a kilometer across, strong enough to withstand the stresses of continuous rotation, is thousands of tons of additional mass. It must spin without rest for centuries, which means bearings that outlast every bearing ever made, and rotating seals, the joints through which air and power and people pass between the spinning wheel and the still hull, that hold tight for longer than any seal in engineering history. Every one of those tons must be accelerated to cruising speed at the start of the voyage and slowed again at its end, so the wheel, like the radiation armor before it, feeds directly into the appetite for fuel. The cure for weightlessness is mass, and mass is the one thing an interstellar vessel can least afford. The links of the chain do not merely coexist, they pull on one another. Life inside the wheel would be its own quiet education. In a rotating habitat, the floor is the outside of the ship, and the ceiling points toward its axis. Weight grows stronger toward the rim and weaker toward the hub, so a tall building in such a world would have lighter upper floors in the most literal sense. A thrown ball swerves. Water pours at a slight, predictable slant. Children raised there would build their deepest physical intuitions, the ones beneath thought, around spin rather than mass, and the honest word for Earth-style gravity, to them, would be a lesson from a textbook. None of this is dangerous in itself. But it is one more way in which the people who arrived at another star would be shaped by the vessel, natives of the crossing rather than of either shore. And the wheel complicates the ship's working life as well. Whenever the engines fire, at departure and at arrival, thrust adds its own direction of weight at odds with the spin, so the great wheel may need to slow and stop for those phases, then be set turning again, an operation involving enormous stored momentum, performed by machinery that must work flawlessly after centuries of idleness. Every mechanism the wheel requires is one more mechanism that must never fail. And even a perfect wheel leaves a question that no one can currently answer. Perhaps the ship cannot afford a full Earth weight and settles for a third of it, or half. What happens to human beings over generations at partial gravity? The plain answer is that nobody knows. No experiment has ever followed mammals through conception, birth, growth, and reproduction at reduced weight, generation after generation. It is possible that development proceeds normally. It is also possible that a growing skeleton needs a full Earth load to form properly, or that some quiet threshold exists below which embryonic development goes subtly wrong, a threshold no one has measured because there has never been a reason or a way to measure it. The ship's designers would have to choose a gravity level for centuries of unborn children, commit the whole architecture to that choice, and sail with no way to correct it if the choice turned out to be wrong. It is worth resting here for a breath, because we have reached the middle of the slow road, and the walk so far can be gathered in a few quiet sentences. The stars are real and worth reaching, and unthinkably far, so far that our fastest machine would need 73,000 years to cross to the nearest one. That distance severs conversation, resupply, and rescue, so any ship must be a sealed and self-sufficient world. Sealed worlds crossing slowly pay in time, and time collects through radiation that cannot be fully shielded, and through the slow unmaking of bodies built for a planet's pull. Each remedy so far, the armor and the wheel, has been paid for in mass, and mass in fuel. That is the pattern of the chain, and it is about to repeat. Because bodies that survive the radiation and keep their strength still need to eat and drink and breathe every day for centuries from a garden that can never once fail. That garden is the next link, and it may be the most delicate machinery on the whole ship, because most of its parts are alive. A generation ship must feed its people, water them, and give them air, every day, for centuries, with essentially nothing lost and nothing brought in. Said plainly, the vessel must recycle everything. Every breath exhaled must become breathable again. Every drop of water must return to the tap. Every scrap of food must be grown from the wastes of the meals before it. Engineers call such a system a closed ecological life support system, a sealed loop in which air, water, and nutrients cycle endlessly among people, plants, and microbes. On Earth, we live inside exactly such a loop and never notice, because ours is the size of a planet. The question the slow road asks is whether the loop can be shrunk to the size of a hull. And the honest answer, so far, is that nothing close has ever been achieved. The most ambitious attempt was a kind of glass world built in the desert, an airtight enclosure covering several acres, containing in miniature nearly everything a planet contains. There was a small ocean with a coral reef, a mangrove marsh, a patch of rainforest, a stretch of savanna, a desert, and a farm, along with living quarters for a crew of 8 who sealed themselves inside with the intention of living indefinitely on what the enclosure could cycle. It was a serious effort, carefully designed, and it remains one of the most instructive experiments ever run, precisely because of what went wrong. Within 2 years, the sealed world drifted out of balance. Oxygen slipped downward, month after month, and no one could say why, because a closed world hides its own bookkeeping. The missing oxygen was eventually traced to an unanticipated culprit, the structure itself. Exposed concrete inside the enclosure was absorbing oxygen through slow chemistry that no one had thought to include in the models. While the air thinned, carbon dioxide climbed beyond what the plants could draw down. The pollinating insects died out, while a species of ant flourished beyond all intention. Crops underperformed, and the crew, though disciplined and committed, lived with steady hunger and the friction that hunger brings. In the end, the world had to be opened, and air let in from outside. Sealed, self-sustaining closure had lasted not centuries, but months. An earlier program, run with characteristic patience on the other side of the world, took a simpler approach. Small sealed cabins where crews lived on recycled air and water and fresh-grown wheat and algae. Those trials achieved closures of about half a year and taught lessons still cited today, including a rule of thumb worth remembering. Closing the water loop is the easiest part. Closing the air loop is harder. Closing the food loop is hardest of all. Later research programs have continued the work, patiently improving individual pieces, waste processing, air revitalization, water recovery, and the pieces genuinely improve. But no one has yet assembled them into a fully closed system that keeps even a small crew alive indefinitely, and the space station does not even attempt the feat. Its recycling systems are excellent, recovering most of each water cycle, and still, the station would become uninhabitable within months if the supply flights stopped. Recovering most is a triumph for a station with deliveries. For a starship, most is just a slower name for failure, because the small losses compound. A loop that leaks 1% a year keeps only a fraction of its water after 2 centuries. Why is closure so hard? Because Earth's version of it is not a machine, but a planet. The biosphere is steadied by oceans that buffer its chemistry, forests that breathe with its seasons, an atmosphere that stirs everything together, and geology that recycles matter over ages, all of it tuned by billions of years of adjustment. That system has size, and size is its secret. A drought here is balanced by rains there. A failed species is replaced from the reserves of a continent. A sealed hull has no reserves and no elsewhere. Every element aboard, every atom of carbon, nitrogen and phosphorus, must cycle from soil to crop, to body to waste, and back to soil, endlessly, without ever accumulating in some unusable corner of the system, or leaking into forms the loop cannot recover. Chemistry does not forgive round-off errors forever. Neither does biology. Small ecologies are unstable ecologies. With few species and small populations, there is no buffer, and single failures cascade. One crop disease, one insect crash, one microbial imbalance in the water system, each capable of pulling on everything else. The living machinery is also pickier than it first appears. Soil is not storage material, but a community. Billions of microorganisms whose balance decides whether roots thrive, and sealed farm experiments have found that keeping soil ecology stable is itself a research problem measured in years, not centuries. The candidate staple crops for ships, wheat, potatoes, soy, algae, each fail in a characteristic way under sealed conditions, some through pollination trouble, some through the slow build-up of pathogens that outdoor agriculture sheds naturally, and at least one, algae, through the quiet mutiny of a crew asked to eat it forever. Even the dormant reserves cost machinery. A ship would carry seed banks against catastrophe, and seed banks need refrigeration, and refrigeration needs power and spare parts, so that even the sleeping half of the garden draws from the ship's mechanical strength. And the air itself keeps its own slow ledger. A sealed hull accumulates whatever its materials exhale, trace gases from plastics and paints and machines, and the scrubbers that clean them are consumable equipment, wearing out in service of an atmosphere that can never once be flushed clean and started over. Scale the garden up to a ship, and the demands become concrete. Feeding a single person entirely from grown crops requires a substantial dedicated area of intensive agriculture, along with the light to drive it, and between the stars there is no sunlight worth the name, so every leaf aboard grows under lamps, and every lamp draws from the ship's power, and the power plant becomes, indirectly, the bottom of the food chain. A community of 1,000 people means fields and tanks and growing racks on the scale of a large farm, sealed inside the hull, tended without pause. Prudent designers would split that farm into several independent sections, isolated from one another, so that a disease or an imbalance in one could be contained while the others carried the load, and that is wise, and it is also the same trade we have met twice already. Redundancy is mass. Separate farms means separate plumbing, separate air handling, separate reserves, more tons to accelerate, and more machinery to maintain. There is also a human truth inside the greenhouse that deserves gentle notice. A farm is not an appliance. It is a practice, a body of judgment about when something looks wrong, held by people who have spent years with the crops, and that judgment must be handed down, teacher to student, along with everything else the ship's library cannot quite contain. The garden, in other words, is not merely a life support system. It is a culture in both senses of the word, and it must be kept alive in both senses at once, continuously, for the entire crossing. Hold the two clocks side by side, and the shape of this link becomes clear. The best sealed world experiment our species has run lasted 2 years before its air went wrong. The generation ship requires the same trick, performed continuously, for 300 years, or 3,000, or 30,000, depending on the engines. The gap between what has been done and what must be done is not a matter of refinement. It is a matter of category, the same kind of gap we met when comparing the road to Mars with the road to the stars. To close it, the designers would be attempting, in effect, to build a small planet from first principles and run it flawlessly on the first try, with no test flight long enough to prove the design, because a fair test of a 3-century garden takes 3 centuries. And the garden, delicate as it is, still needs something beneath it. Pumps to move its water, fans to stir its air, lights, sensors, valves and power, day and night, for the whole of the voyage. The living loop rests on a mechanical one, and machines have their own way of keeping time. That is the next link in the chain, and it comes with a question that sounds almost childlike and has no comfortable answer. What, exactly, keeps running for 300 years? Nothing human beings have ever built runs for centuries without repair. That sentence sounds sweeping, but it survives every test you put to it. The oldest working machines in the world are curiosities, clocks and engines kept alive by devoted caretakers who replace their parts as they fail, which is to say, machines that run for centuries only because a river of new components flows through them. Museum conservators fight constant, patient battles just to keep century-old machinery presentable, let alone operable. Our own most durable creation makes the point best of all. Voyager 1, the longest-serving spacecraft in history, is a masterpiece of reliability, largely solid state, no moving parts to speak of, built by careful people at the top of their craft. It has endured for nearly 50 years, and it has done so by amputation. Its power comes from the steady decay of a lump of plutonium, and the heat of that decay fades on a fixed schedule, costing the spacecraft about 4 watts of electricity every year. As the budget shrank, its keepers switched off instrument after instrument, heater after heater, choosing at each step what the spacecraft could live without. Today it runs on power that would barely light a few bulbs, and within a few years, there will not be enough to run anything at all. Voyager will fall silent, not because anything struck it, but because its heart source ran down exactly as physics said it would. Our finest machine, in the gentlest environment imaginable, will have lasted half a century. The slow road asks for 5 times that, or 50 times, or 500. On Earth, complex machines persist for a different reason than good design. They persist because supply chains persist. A jet engine endures tens of thousands of flight hours because it is inspected constantly and its worn blades are replaced with new ones, made in factories, from metals refined in mills, from ore dug out of the ground, by an industrial web involving millions of people. Every durable machine you have ever trusted is really a partnership between the machine and a civilization standing behind it. A generation ship has no civilization behind it. It carries whatever it launched with, and the moving parts aboard, the pumps, fans, valves, compressors and bearings on which the sealed garden and everything else depends, have working lives measured in years or decades, never in centuries. Electronics fare no better over such spans, accumulating radiation scars until they fail. Even software ages, in its peculiar way. Formats fall out of use, programming languages are forgotten, and the people who truly understood a critical system retire and die, on Earth within decades, and a ship's systems must outlive many such lifetimes. Redundancy, the engineer's first instinct, helps less than hoped. Carrying 2 of everything doubles the mass, and the deep failures, corrosion, radiation, a flaw in the design itself, take both copies for the same reason. The only real answer is for the ship to become its own supply chain, to carry not just spare parts but the ability to make parts, machine shops, foundries, chemical works, perhaps the means of fabricating electronics. And the moment the ship becomes a factory, it needs what every factory needs, which is skilled people, in every generation, without exception. Here the mechanical barrier quietly becomes a human one, and the human record on this point deserves to be taken seriously, because it is longer than the engineering record and no more comforting. Knowledge dies. It dies more easily than seems possible. After the collapse of the great empire of the ancient Mediterranean, the recipe for its concrete, a material so good that structures made from it still stand after 2,000 years, simply vanished and stayed lost for more than 1,000 years. The aqueducts that had watered its cities kept standing, visible to everyone, while the knowledge of how to maintain them evaporated, and cities that had enjoyed running water for centuries went back to wells and rain. The Polynesian wayfinding tradition, which had guided voyages across the widest ocean on Earth for thousands of years, was carried entirely in living memory, master to apprentice, and when outside contact disrupted that chain of teaching, most of the tradition slipped away within about 3 generations, surviving only in fragments held by a handful of aging navigators. And in our own era, the people responsible for burying long-lived hazardous waste have spent decades on a strange and humbling question: how to write a warning that will still be understood in 10,000 years, and have concluded that it may not be possible because no language and no symbol system has ever held its meaning that long. Now set the ship's requirement against that record. A generation ship does not need to transmit a warning across the centuries. It needs to transmit an entire technical civilization: metallurgy, chemistry, medicine, electronics, agronomy, mechanical repair, dozens of disciplines, each demanding years of training, each depending on the others, through an unbroken chain of teachers and students, with no outside contact, no fresh experts arriving, and no possibility of rediscovery, because there is no neighboring culture to relearn from and no ruin to excavate. The ship's library can hold every instruction ever written, but skills are not instructions. Surgery lives in supervised hands. Welding lives in practice. Troubleshooting lives in judgment, built from 1,000 small failures. If any single generation, for any reason, fails to raise enough machinists, or enough chemists, or enough surgeons, the loss does not announce itself at once. It waits and compounds, and presents itself years later as a system no one alive can fix. On the slow road, what is lost stays lost. And a generation is not a machine that can be commanded to learn. It is people living their one life in a corridor. The long confinement studies conducted on Earth, in which volunteer crews sealed themselves into simulated ships for over a year, found what honesty would predict: disrupted sleep, low moods, withdrawal, friction between crewmates, and this among elite volunteers who chose the mission and knew the date the door would open. Aboard a generation ship, the middle generations never chose, and no door opens. They inherit a purpose, selected by ancestors they never met, on behalf of descendants they will never meet, and they must maintain, with daily discipline, systems whose reward arrives after their own deaths. History offers little comfort about how purpose weathers such spans. Isolated communities drift, in language, in belief, in what they hold important, within a few generations. On Earth, that drift is simply culture doing what culture does. On the ship, where the founding purpose is also the maintenance schedule, drift can be fatal, and if factions form, the losers of any quarrel cannot leave, and everyone still shares the same air. Every durable institution in history has been renewed from outside, by trade, by rivals, by newcomers, by the pressure of a wider world. The ship has no outside. It must renew itself from within, perfectly, every generation, for as long as the crossing lasts, and no human community has ever done it. This, finally, is what the minimum population numbers were really about. 500 to 5,000 people is not just a genetic threshold. It is an occupational one, enough people to fill every critical trade, every generation, forever, with no gaps. A village asked to be a civilization, and to stay one, in a can, in the dark, for centuries. The village faces one more inheritance problem, written not in its libraries, but in its cells. A founding population of hundreds or a few thousand carries only a slice of humanity's genetic variety, and in a sealed community, that variety erodes with every generation. Rare, harmful traits, scattered thinly and harmlessly through a large population, begin to pair up in a small one, surfacing as reduced fertility, weakened immunity, and quiet developmental troubles. Managing that erosion across centuries means guiding who may have children with whom, generation after generation, a level of intimate governance no human society has ever sustained or would likely accept. The alternative is to carry frozen reserves, banks of preserved genetic material, to refresh the line along the way, And here the engineering record speaks softly again. Preservation of that kind has been demonstrated across decades. The voyage asks for centuries, and no biological sample in history has yet been kept viable for 300 years, because 300 years ago, no one had the means to try. Like the sealed garden, the frozen bank also rests on machinery, on refrigeration that must never fail and power that must never lapse, so that even the ships unborn are, in the end, wards of its pumps and reactors. So the slow road, walked to its end, is a single long lesson in coupling. The armor against radiation adds mass. The wheel that preserves the body adds mass and mechanism. The garden that feeds everyone rests on machines. The machines rest on skills. The skills rest on a society. The society rests on purpose, and purpose is the one cargo that cannot be crated and stowed. Suppose, even so, that all of it holds. Suppose the shielding suffices and the wheel never ceases, the garden never stumbles, the teachers never fail, and the village steps off the far end of centuries still whole and still willing. Every one of those triumphs is then handed to a final examiner, the destination itself, a world chosen by telescope centuries before, from 4 light-years away. What that examiner can do to a perfect voyage is the next part of the story. Everything the generation ship endures is endured for the sake of a place, and the place is known only through telescopes. That is worth saying carefully, because telescopic knowledge is real knowledge, and also a very particular kind. When astronomers call a distant world promising, they mean that its size and mass suggest rock, that its orbit sits in the band where water can stay liquid, and perhaps that starlight filtered through its atmosphere shows the signatures of interesting gases. All of that can be measured honestly across trillions of miles, and it is a triumph that it can. But consider everything such measurements cannot touch. A spectrum cannot say whether the surface below is stone or magma. It cannot report the acidity of the oceans or the chemistry of the soil, or whether the planet hosts a native microbiology, and if so, whether that biology is compatible with ours, indifferent to it, or quietly lethal. It cannot describe the weather across a year, or the climate across a century, or how often the planet's star lashes it with flares. It cannot even promise land. A world that reads as rocky by its density may be an ocean without shores, its water running down for 100 kilometers before touching anything solid. The most careful habitability case ever assembled from starlight still rests, in the end, on a handful of absorption lines, a shadow of a shadow, read with great skill. We know how much room that leaves for surprise, because we have been surprised before, inside our own solar system, where the distances are trivial and the observing conditions are as good as they will ever be. Before any spacecraft visited the cloud-wrapped planet next door, respectable scientists imagined a warm, wet world beneath the clouds, perhaps swamps, perhaps oceans. And the reality was a surface hot enough to melt lead under a crushing atmosphere laced with acid. Before landers reached Mars, models allowed for accessible water and a friendlier ground than the arid radiation-scoured plains the rovers actually drove across. Every planet and moon our probes have ever reached turned out to differ from its telescopic portrait, often radically. There is no reason to expect worlds 4 light-years away to be more faithful to their portraits than worlds 4 light-minutes away have been. The gases themselves can mislead, even when they are read perfectly. Oxygen is the example astronomers return to, because it feels like the surest fingerprint of life, and it is not. A lifeless world can build an oxygen-rich sky through nothing but slow chemistry, as relentless starlight splits water vapor apart and the light hydrogen leaks away to space, leaving the oxygen behind like salt after evaporation. Around certain stars, that process can run for ages, dressing a dead planet in the atmosphere of a living one. So even the most hoped-for signal arrives with an asterisk. The natural remedy would be to scout, to send a robotic probe ahead and let it report back before anyone commits a ship full of generations. But the arithmetic of the earlier parts of tonight closes that door with a certain irony. A scout we can actually build travels at Voyager speeds, and its report would arrive in 70,000 years. A scout fast enough to be useful would require the very propulsion revolution whose absence is the reason for the generation ship in the first place. And even a fast scout's verdict ages during the centuries the big ship then spends in transit. The slow road cannot see where it is going and cannot wait to find out. And even a perfect portrait ages. The light a telescope gathers left the planet years before the observation, and the ship then flies for centuries. Stars flare and settle. Atmospheres thin. Orbits shift by small resonant nudges. Climates wander on their own schedules. The processes that reshape a world operate on exactly the timescales the voyage occupies, which means the crew is not traveling toward a place. It is traveling toward a photograph, and the photograph may be centuries out of date on the day of arrival. The tidally locked worlds around red dwarf stars sharpen the point. Such a planet may hold its habitability in a single ring of eternal sunset between the burning hemisphere and the frozen one, and the width and kindness of that ring depend on winds and oceans no spectrum can resolve. A star that looks calm in the snapshot may, across millennia, be a stormy one, stripping ozone and air from the very world the ship is bound for. If a biosphere is already present, the questions grow stranger. An alien microbial ecosystem might be harmless. It might be incurably hostile to Earth biology. And it would transform the ethics of arrival entirely, because a living world is not an empty lot, and sterilizing one is not an option anyone could defend. Now set this uncertainty against the ship's central limitation, which is that it cannot hedge. A generation ship carries no fuel for a second destination. The trajectory is committed at launch, worked out centuries in advance, and there is no turning around, because turning around is simply another interstellar voyage with nothing left to make it. If the world at the far end proves uninhabitable, the mission does not fail gracefully, or partially, or with lessons learned. It fails absolutely at the finish line after every test was passed. Centuries of radiation endured, machines maintained, gardens kept in balance, knowledge handed faithfully down, generations born and buried in transit, and at the end of all of it, a world that cannot be lived on and no means of going anywhere else. The people who chose that risk are not the people who pay for it. The choosers died in the first generation. The payers are descendants who inherited the wager along with the corridors. There is one more turn of the screw, gentle and strange. Suppose the world is kind after all. The arrivals may no longer be entirely suited to it. A population shaped for centuries by the ship, by its chosen gravity, its filtered light, its closed microbial world, its air held at whatever mixture the garden could sustain, would meet a planet the way islanders meet a continent, vulnerable in ways no one can fully predict. Their bodies would be natives of the crossing. Their immune systems would know only the ship's small, closed roster of microbes, and a whole living planet's worth of unfamiliar biology would be waiting at the bottom of the ladder. Even a perfect destination would be, for them, an alien one, and the first years on its surface might be the most dangerous chapter of the entire voyage. And with that, the slow road has been walked to its end, and its deepest flaw can be stated in one quiet sentence. Every single hazard along it grows with time, and the slow road is made of time. The radiation dose grows with the years. The garden's drift grows with the years. The wear, the forgetting, the fraying of purpose, the aging of the destination photograph, all of it grows with the years, which means the voyage cannot be rescued by adding more of the very thing that is destroying it. Slowing down makes every link tighter. And so the mind does what minds do and turns to the opposite door. If centuries are the poison, then abolish the centuries. Go fast. Compress the crossing into decades or years so that one crew departs and the same crew arrives, and the generations, the gardens, and the long forgetting never have their chance. It is the obvious answer, and it is a real one, honestly grounded in physics. Speed genuinely does dissolve almost every barrier the slow road raised. What it cannot dissolve is the price tag, because the universe prices speed in a currency of its own, and the numbers on that price tag are unlike anything we have met so far tonight. The fast road is next, and it begins with the simple question of what it costs to make something move that quickly. The fast road opens with a piece of physics so familiar that it hides its own strangeness. Motion costs energy, and the cost climbs with speed. In everyday life, the climb is already steeper than intuition expects. Double the speed of a car, and its energy of motion does not double. It quadruples, which is why modest increases in speed make such immoderate differences in a collision. That square law relationship holds beautifully for baseballs, automobiles, and spacecraft at the speeds we currently manage. But as speeds climb toward a meaningful fraction of the speed of light, the law itself begins to bend, and it bends in the unkind direction. Relativity, confirmed by more than a century of experiment, describes what happens. The closer an object comes to the speed of light, the more energy each further increment of speed demands, and the demand does not level off. It curves upward, steeper and steeper, toward infinity at the light barrier itself. There is no clever route around this curve. It is not a property of engines. It is a property of motion. Put numbers to it, gently, and feel the ground shift. Take a spacecraft of 10,000 kilograms, roughly the mass of a large truck, and imagine it cruising at 1/10 of the speed of light. The energy of motion it carries at that speed is comparable to the detonation of 1,000 megatons of explosive, which is to say, roughly 20 times the yield of the largest device ever detonated on Earth. That is the energy content of one small unmanned vehicle, merely moving. And a truck is not a starship. A crude vessel with its shielding, its spinning wheel, its sealed garden, its workshops and reserves, masses hundreds of tons at the barest minimum, and more honestly, hundreds of thousands of kilograms. Scale the energy to match, then raise the speed, because 1/10 of light speed still means a crossing of more than 40 years. At half the speed of light, the energy budget of a modest crude ship rivals the total energy that all of human civilization, every power plant, every engine, every furnace on Earth, produces in 2 to 3 years. At 90%, the figure climbs past 20 years of global output, poured into a single vehicle. And these figures assume that every unit of energy is converted into motion perfectly, without waste, which physics forbids. Real engines squander. The true bill is always higher. That is the energy wall, and it is only the first toll booth on the fast road, because knowing how much energy a speed requires says nothing about how a ship actually acquires it. Rockets acquire it by carrying fuel, and here the fast road meets its oldest and most patient adversary. The relationship was worked out more than a century ago, and it is usually called the rocket equation. A rocket pushes itself forward by throwing mass backward, which means it must carry the mass it will throw, which means the fuel at the start of the journey must accelerate not only the ship, but all the fuel to be used later. Fuel to push fuel, and fuel to push that. The consequence is exponential, and exponential is a word worth taking seriously. The fuel a rocket needs does not grow in proportion to the speed desired. Roughly speaking, doubling the target speed squares the required ratio of fuel to ship, and tripling it cubes the ratio. For low speeds, the penalty is manageable, which is why rockets work at all. For interstellar speeds, the penalty becomes something close to a joke told by mathematics. Chemical rockets, with their exhaust streaming out at 3 to 5 kilometers per second, cannot reach even 1% of light speed under any arrangement whatsoever, because the fuel required would outweigh everything available to burn, and the phrase, everything available, is meant cosmically. The equation forbids it, absolutely, no matter the engineering. Ion drives, with exhaust 10 times faster, shift the numbers without changing the verdict. The serious candidates begin with fusion, the process that powers the stars themselves, fusing light nuclei and releasing energy far beyond chemistry. A fusion drive, if one could be built, might stream exhaust at several hundred kilometers per second, perhaps towards 700 at the optimistic edge. That is roughly 100 times better than chemical rockets, and it drags interstellar arithmetic out of the absurd and into the merely enormous. But even fusion bows to the equation. Work the numbers for a crude vessel of realistic mass aiming at several percent of light speed, and the required fuel load comes back in ratios of thousands to one and far beyond, mountains of fuel per ton of ship, with every added ton of shielding or garden multiplying the mountain. And this is arithmetic performed on an engine that does not exist. Sustained fusion with more energy out than in has only just been coaxed into existence in laboratories, in bursts, in machines the size of buildings. No fusion engine has ever flown. The nuclear pulse vessel we met on the slow road, riding its chain of detonations, remains the highest performance propulsion ever seriously engineered, and its ceiling was a few percent of light speed, which is why it belonged to the slow road in the first place. One fuel, and only one, truly breaks the equation's grip on paper. Antimatter. When a particle of matter meets its mirror twin, the two annihilate completely, and nearly all of their combined mass becomes energy, a conversion thousands of times more efficient than fusion and billions of times beyond chemistry. A ship burning antimatter could, in principle, reach deep into relativistic speeds with a fuel tank of sane proportions. The physics is real, and that is where the good news ends. All the antimatter humanity has ever produced, across every accelerator laboratory on Earth, across decades of effort, amounts to less than 100 billionths of a single gram. The most advanced facilities can now assemble a few tens of thousands of anti-atoms in a session, a number that sounds large until you recall how many atoms make a gram, at which point the gap between what we can make and what a ship would burn opens to more than 20 orders of magnitude, the difference between a raindrop and an ocean. Producing the stuff costs billions of times more energy than the fuel then contains, so an antimatter economy would first require an energy economy beyond anything imagined. And storing it may be the hardest part of all, because antimatter touches nothing. It must be suspended in electromagnetic traps in perfect vacuum forever, since the first contact with an ordinary atom is annihilation. Current traps hold atom-scale quantities for hours. A starship's tank would hold kilograms for decades. No design on paper convincingly bridges that gap. It is worth being precise about what kind of barrier the energy wall is, because it differs from every other obstacle in tonight's chain. Most limits in engineering are limits of craft. Better materials, better designs, and better tools push them back, decade by decade, and the history of technology is the history of that pushing. The energy wall is not that kind of limit. No refinement of engines changes how much energy a given mass moving at a given speed must carry, any more than clever accounting changes a sum. Technology can improve how efficiently stored energy becomes motion, and that matters enormously at the margins, but the total on the invoice is fixed by the universe, printed in the relationship between mass, velocity, and light. A civilization that wished to pay such invoices routinely, launching crewed ships at large fractions of light speed, would need command of energy on a scale far beyond planetary, harvesting its star rather than its fuels. Nothing forbids such a civilization in principle, but it would not be a version of us with better rockets. It would be a different kind of thing altogether, and its problems would still include every one that follows. And one more toll waits quietly at the end of the fast road, easy to forget and impossible to avoid. The ship must stop. A vessel that cannot shed its speed does not arrive at the new world. It passes through the destination system in hours, a streak of hardware moving at cosmic speed, gathering what data it can, as everything it traveled decades to reach falls behind forever. Stopping requires undoing every bit of velocity so expensively purchased, which doubles the energy bill outright, and does something far worse to the fuel arithmetic, because the fuel for braking must be carried, unburned, through the entire acceleration, which means the outbound engines must push it, which means more outbound fuel to push the braking fuel, and the exponential penalty applies to the whole stack twice over. Some designs try to dodge the doubling, using an immense magnetic field as a parachute against the thin interstellar gas, braking without fuel. The idea is sound physics, and it calls for superconducting loops kilometers across, functioning perfectly after decades of relativistic battering, which returns us to familiar territory, a solution that is itself a barrier. This is the fast road so far, and we have not yet left the launch pad in good order. The energy is civilizational. The fuel is exponential. The braking doubles both. And the road itself, the seemingly empty space ahead, has not yet said a word. It speaks next, and its voice is the strangest part of the whole story. Earlier tonight, the emptiness between the stars was a comfort of sorts. One hydrogen atom per cubic centimeter, a vacuum finer than any laboratory can make, a nothing so pure it nearly perfects the word. Voyager 1 has been drifting through that nothing for decades and has not been troubled by it in the slightest, because at 17 kilometers per second, the interstellar medium is functionally not there. Here is the strange turn at the heart of the fast road. That same medium, unchanged, becomes one of the most destructive environments a machine has ever been asked to survive, and the only thing that changes is the speed of the ship passing through it. The void has no malice and sets no trap. It simply keeps its few atoms and its scattered dust where they have always been, and lets the traveler's own velocity do the arithmetic. Begin with the dust. Interstellar space carries a thin population of solid grains, most of them smaller than the width of a human hair, ancient soot and mineral flecks shed by dying stars, drifting for millions of years. At Voyager speeds, a ship could fly through them forever and collect nothing worse than a faint patina. Now raise the ship's speed to 1/10 of the speed of light, and consider a single grain with a mass of 1 milligram, small enough to rest invisibly on a fingertip. In the ship's reference frame, that grain arrives carrying hundreds of millions of joules of kinetic energy. For comparison, a bullet from a powerful handgun delivers several hundred joules. The dust grain strikes with the concentrated energy of hundreds of thousands of such bullets arriving together at a single point. There is no material response to call that a collision. It is a detonation. The grain and a patch of hull convert to vapor and plasma in an instant, leaving a crater rimmed with melted material. Careful modeling of relativistic flight has reached calm, specific conclusions about the accumulation. Across a 4-light-year crossing at 1/5 of light speed, the steady rain of ordinary dust erodes, melts, and vaporizes measurable depths of material off the entire forward-facing surface, and the leading face of the vehicle runs hot for the whole crossing, warmed by the continuous bombardment of gas atoms alone. At half of light speed, each impact grows roughly tenfold in energy, and a 1-milligram grain arrives like a large conventional bomb. And the grains are only the smallest members of a family. Between micron dust and the small asteroids our telescopes can track lies a population of ice fragments and pebbles that cannot be detected from light years away, and cannot ever be, because nothing that small announces itself across such distances. A ship crossing for decades at high speed sweeps out an enormous corridor of space, and the statistics of that corridor make an encounter with something far larger than dust genuinely plausible. At half of light speed, a pebble delivers the energy of a nuclear weapon. Nor can the ship dodge. At those closing rates, by the time any sensor detects an object ahead, the object has already arrived. The medium is also not smooth. The sun happens to drift through a thin, warm local cloud, and any real route to a neighboring star crosses regions of differing density that cannot be fully mapped in advance, so the ship samples its hazards blind, at full speed, the entire way. Then there is the gas itself, and this may be the strangest passage in tonight's whole story. A hydrogen atom at rest in space is the mildest object imaginable. But motion is relative, and in the reference frame of a ship moving at relativistic speed, every atom in the road ahead is a particle arriving at relativistic speed. At 1/10 of light speed, each incoming proton carries energies comparable to the particles used in radiation therapy. At half of light speed, the energies match those of major research accelerators. The forward surface of the ship experiences, continuously, something with no natural precedent, a particle beam of accelerator intensity, generated by nothing but its own motion through the thinnest gas in nature. The dose grows steeply with velocity, and the arithmetic lands in days, not years. At half of light speed, an unshielded crew positioned behind ordinary structure would receive lethal exposure within days. Let the full irony of that settle gently. The fast road was chosen to escape the slow accumulation of radiation over the centuries, and at speed, the escape route generates its own radiation storm, harder and more concentrated than the one left behind, with the dose rising as the square of the very speed that was meant to save everyone. The defenses on offer are real, and each one hands its bill to a link we have already visited. A massive sacrificial shield can ride ahead of the ship, a thick plate of expendable material that absorbs the dust and erodes across the voyage, and its thousands of tons feed straight into the rocket equation: fuel to push the shield, fuel to push that fuel. Layered bumper shields of the kind that protect today's spacecraft, thin outer skins that vaporize incoming grains so the debris sprays harmlessly against an inner wall, work beautifully at orbital speeds and are simply overwhelmed at relativistic ones. A magnetic deflector can sweep the charged component of the oncoming storm aside at the cost of enormous continuous power, and it does nothing against neutral atoms or dust, which carry no charge for a field to grip. And the erosion is not even distributed fairly. It falls hardest on precisely the equipment that must face forward, the sensors and antennas by which the ship sees and navigates, so the voyage blinds itself preferentially, wearing away its own eyes. The oncoming storm also revives an old acquaintance from the slow road. When those relativistic protons and helium nuclei strike the ship's forward shielding, they shatter atoms in the material and spray secondary particles onward into the structure. The same spallation cascade that made thick metal walls treacherous against cosmic rays, now driven not by the galaxy's occasional messengers, but by the ship's own continuous headwind. The secondaries claw at electronics as well as at flesh, flipping stored values and burning microscopic channels through the radiation-hardened chips, so the computers that fly the ship age fastest, exactly when the flying is most delicate. Meanwhile, the absorbed energy has to go somewhere, and it goes into heat. The leading structures of the vehicle settle into a permanently elevated temperature, glowing gently with the warmth of their own passage, and the ship must carry radiators to shed that heat, and the radiators are mass, and the mass is fuel, and by now that sentence completes itself. Even the mathematics of exposure works against the traveler in a small, sly way. Doubling the speed halves the years spent in the storm, but far more than doubles the storm's intensity, so the total dose of the voyage rises with speed rather than falling. Going faster to spend less time in danger increases the danger faster than it shrinks the time. Two more constraints close over the fast road like quiet parentheses. The first is the body's tolerance for acceleration. Human beings can live comfortably under sustained thrust equal to 1 Earth gravity, and not much more, since at twice that level every movement doubles in effort, and sleep itself becomes labor, while sustained higher loads injure. At 1 gravity of continuous thrust, reaching 1/10 of light speed takes about 35 days of burning, and reaching half takes the better part of 7 months, every second of it spending fuel at the exponential rates we have already priced, because slow, gentle burns mean carrying the fuel longer, and the equation punishes carrying. Accelerate harder to save fuel, and the crew breaks. Accelerate softer to spare the crew, and the fuel mountain grows. There is no comfortable setting on that dial. The second constraint is the mirror of the first. Whatever was done to speed up must be done again to slow down, months more of burning, and the braking phase arrives with its own special unpleasantness, because the ship decelerates nose first into the oncoming medium, engines toward the destination, plowing through the dust storm at the highest speeds of the voyage, precisely when its shielding is most worn. The fast road, walked honestly, ends where the slow road ended, in a lattice of couplings. Speed buys freedom from time, and pays for it in energy, dust, radiation, and thrust that the body can barely carry. And there remains one wall we have mentioned only in passing, the one that stands at the end of every road, patient and absolute. The speed of light itself. That wall, and the strange gift folded inside it, is where we go next. Every road we have walked tonight ends at the same horizon, and it is time to look at it directly. The speed of light is not a speed limit in the way a road sign is a speed limit, a number that could be exceeded by anyone willing to accept the consequences. It is a structural feature of the universe, woven into the relationship between mass, energy, and time. As an object with mass approaches the speed of light, the energy required to push it faster grows without bound, and at the limit itself, the requirement becomes infinite. Not enormous. Infinite. This is not a theory awaiting its test. It is measured, routinely, in the great particle accelerators, where protons are driven to within a whisper of light speed, each one carrying thousands of times its resting energy, and where no proton, in all the years of trying, has ever reached the limit, because the limit is not a place. It is the edge of what motion means. And even standing respectfully just beneath it changes less than one might hope. At 99% of the speed of light, the nearest star remains over 4 years away, the center of our galaxy 26,000, and the nearest large galaxy beyond 2 million. Relativity does fold one strange gift into the wall, and it deserves an honest look, because it is often offered as the loophole that saves the dream. Time aboard a fast ship runs slow, relative to the world left behind. At 90% of light speed, a crew ages at a little under half the rate of the people at home. At 99%, 1 year passes aboard for every 7 on Earth, and closer still to the limit, the ratio grows without end. In principle, travelers moving fast enough could cross enormous distances within their own lifetimes, arriving alive and sane while centuries pour past outside the hull. The physics is real, and the arithmetic is honest. What the arithmetic buys, though, is stranger than it first appears. Consider a crew sent to a star 40 light-years away at 95% of light speed. From Earth's calendar, the round trip consumes about 85 years. From the crew's, about 27. They return still in middle life, to a world where everyone who chose them, trained them, and loved them has died, where the language has shifted beneath their feet, where the agencies that sent them have dissolved and reformed under new names with new purposes, and where their hard-won reports concern questions that were closed, one way or another, before they landed. Their messages home, sent along the way, stretched and reddened by their speed, arrived at receivers rebuilt 3 times over, describing a mission context aging at a different rate at each end of the conversation. Time dilation does not cancel the cost of the crossing. It moves the cost onto everyone who stays, and it severs, gently and completely, the thread between the travelers and the civilization they were traveling for. They become exiles in time, moving through the universe at a different rate than their own species. And the gift only becomes meaningful at speeds above 90% of light, exactly the regime where the energy wall is steepest, the dust strikes hardest, and the self-made radiation storm burns brightest. The loophole opens only at the center of the fire. It is fair, before the chain is judged, to hear the counter-proposals, because serious people have spent careers on them, and each one teaches something. Fusion drives, we have seen, are real physics awaiting unreal engineering, and even perfected they compress the voyage from tens of thousands of years to centuries, delivering the traveler back to the slow road's mercies. A famous older idea proposed doing away with fuel tanks altogether, scooping the interstellar hydrogen ahead of the ship into an immense magnetic funnel and fusing it on the fly, an engine feeding on the road itself. The elegance is genuine, and the arithmetic is not kind. The medium is so thin that the funnel must stretch hundreds or thousands of kilometers. The power to maintain it is enormous, and the careful analyses agree on a quiet verdict that at high speed, the drag of gathering the fuel exceeds the push of burning it. The scoop is a brake wearing an engine's clothing, and the fuel source and the hazard turn out to be the same thin gas. More recently, and more practically, there are the light sails, gram-scale spacecraft accelerated to 1/5 of light speed by ground-based laser arrays of extraordinary power, chips with cameras riding beams of light. Nothing in physics forbids them, and something in their scale instructs. The laser array required rivals the combined output of hundreds of power stations, focused with impossible steadiness on a sail meters wide, and what it sends to the stars is a postcard camera, no crew, no brakes, no return, a flyby lasting hours after a crossing lasting decades. The one concept that entered engineering reality did so by shrinking the traveler to almost nothing and leaving every human being at home. Each proposal, examined closely, solves some links of the chain and hands its savings to the others. Fusion buys speed and pays in fuel mountains. Antimatter buys the fuel arithmetic and pays in a substance the universe barely permits us to make. sails by the fuel problem entirely and pay in payload, carrying nothing that lives. Nothing severs every link, because the links hold one another. And that is the strange reason in this episode's title, stated at last in full. Interstellar travel is not forbidden by any single law. You will find no equation that says no ship may cross. What stands between us and the stars is quieter and stronger than any single prohibition, a chain of constraints, each rooted in ordinary physics, each coupled to its neighbors, so that every solution is a payment into an adjacent problem. Distance forces duration or speed. Duration destroys bodies, gardens, machines, knowledge, and purpose. Speed devours energy, summons the vacuum itself as a weapon, and runs, at last, into a wall built from the structure of motion. Shielding is mass, mass is fuel, fuel is more fuel, braking doubles everything, and the light barrier caps the whole ledger with infinity. The universe did not build one wall between us and the stars. It built a chain, and the weight is distributed, and the structure holds. Some will ask, reasonably, about the ideas that step outside the chain altogether, the proposals to bend space itself rather than cross it, carrying a ship inside a moving fold of geometry so that nothing ever outruns light locally while the fold does the traveling. These are not fantasies. They are solutions to the real equations of gravity, studied soberly in the literature, and the equations themselves deliver the verdict with their usual composure. Sustaining such a fold requires a form of energy that is, in effect, negative, a kind of substance that pushes where all known matter pulls, and while whispers of related effects exist at microscopic scales in the laboratory, nothing observed in nature supplies it in usable quantity, or suggests how anything could. The fold remains mathematics, beautiful and unbuilt, a reminder that the universe permits us to describe far more than it permits us to do. And notice what even the dream of the fold concedes. It does not argue that the chain can be broken. It proposes to leave the road entirely, because everyone who has priced the road agrees on what it costs. Yet, the claim must be kept precise, because precision is a kindness here. Physics does not forbid our things from going. 2 of our machines are in interstellar space at this moment, alive after a fashion, whispering home. Small robotic probes may follow within generations, photographing other suns for the descendants of the people who launched them. Exploration is permitted. Knowledge is permitted in almost unlimited measure. From exactly where we stand, we can read the atmospheres of worlds we will never touch, weigh galaxies we will never cross, watch planets form around infant stars, and trace the history of the universe back to its first bright hour. Light crosses the gulf for free, in mere years, and brings us everything it touches. What the chain withholds is presence, the warmth of a human hand on another world's stone. Postcards, not passages. And perhaps, held gently, that is not only loss. The universe was built at a scale where stars keep their distances, and the same architecture that holds them apart holds them steady, burning patiently for billions of years, pouring their light into the dark, where anyone with eyes may gather it. Voyager 1 is still out there as you drift towards sleep. It is moving at 17 kilometers per second through the space between stars, and nothing ahead will slow it for billions of years. Its power fades by 4 watts a year, and within a few years its voice will fall below hearing, and it will go silent, still traveling. In roughly 40,000 years it will pass within a couple of light years of another star, and it will not stop there, or anywhere. It carries a golden record, fixed to its side, holding greetings in dozens of human languages, music from many centuries and many cultures. the sound of rain, the sound of a heartbeat, and the recorded brainwaves of a person thinking about love. No one will ever play it. The distances are too great, and the silence is too deep, and the little craft will outlast every monument on Earth, carrying its message like a letter written to no address, sent anyway, because sending it was the human thing to do. That, in the end, may be the truest shape of our relationship with the stars. We cannot go. We can know, and we can wonder, and we can send our voices ahead of us into a dark that keeps everything it is given. And so the stars remain where they have always been, burning quietly at distances the universe never meant to be crossed, while our small machines drift outward, carrying songs no one will hear. There is a strange peace in a boundary this absolute. Nothing is asked of you tonight but rest. Let your breathing slow. Let the distances hold everything in place. Sleep well and good night.